ACLs are a versatile tool, which can be used for many different purposes. But while they have many uses, their most obvious function is as a packet filter. That is, to allow or deny traffic. Packet filters add security to the network. Perhaps we want to limit the workstations that are allowed to log onto routers, or maybe we want to allow only HTTPS traffic to a server. We can use ACLs in both cases, to allow some traffic, but to deny others. An ACL is really a collection or list of rules. Each of these rules is called an access control entry, or ACE, and is used to permit or deny traffic. Each entry in the list is evaluated in order, from the top of the list to the bottom. Every entry contains some match criteria. This may include information like source address, destination address, protocols such as TCP and UDP, and port numbers. When a packet comes into a router, the router will look at this information in the packet header. It will compare this against each entry in order to see if it matches any of the rules. If the router finds that the packet matches one of these entries, it will then look at the action. The simplest actions are permit and deny. As you would expect, if the action is permit, the traffic is allowed through. If the action is deny, the router will block the traffic. It's important to understand that each rule is evaluated in order. See how there's a number next to each entry? That's the sequence number. This number determines the order the rules are evaluated in. As soon as an incoming packet matches one of these entries, the action is applied. At this time, the router stops evaluating more rules. The key point from this is that the first match wins. So when you create ACLs, it's important to consider the order of the rules, otherwise you may not get the results you want. But what happens if none of our entries match incoming traffic? There's an invisible rule at the end of the list called the implicit deny. When the entries we've configured don't match, the implicit deny entry will drop the traffic. Is this a good thing? Yes, it is. We can't think of every rule to cover every possible scenario. Aside from making our jobs too hard, it would make our ACLs far too complicated. So, for security, if we're not expecting the traffic, the router will drop it. If you're really observant, you may have seen that some of these masks look backward. No, it's not a mistake. And this is not a subnet mask, although it does look similar. This is a wildcard mask. The subnet mask that you're used to uses binary ones and zeros to show which part of an IP address is the network and which part is the host. You can check out the How IP Addressing Works video if you'd like a refresher on this. A wildcard mask, on the other hand, is used to match addresses. The zeros refer to the parts of the address that need to match the address in our rule. The ones are the parts that don't need to match. So in the example above, the wildcard mask says that we're looking for any IP address that starts with a 192.168.10. We're also saying that we don't care what the fourth octet of the IP address is. So the address 192.168.10.12 will match our rule. However, 192.168.22.1 will not match. This probably raises a question in your mind. Why do we bother using wildcard masks at all? Couldn't we just use a subnet mask? Well, a wildcard mask does have an obscure advantage. A subnet mask requires all the ones and the zeros to be grouped together. A wildcard mask, though, does not have any such restriction. This means that we can perform some advanced matching by mixing up the bits which are turned on or off. In the example here, the 192.168 part must match, as those bits in the mask are set to 0. Also, the .1 at the end needs to match as well. But the third octet can be anything at all, as this is where the wildcard bits are. So 192.168.10.1 will match, but 192.168.10.2 will not. Why would we ever want to do this? Granted, there are rare cases, but think of a case where we have several subnets, and the router in each one uses the .1 address. An ACL like this could be used to allow management traffic to the router, but deny it to everything else. If you can think of a few examples like this, please share them in the comments below. This type of ACL is called an extended ACL. This is only one type of ACL. There are also several others. Each of these have a different functionality, but as this video is an introduction to ACLs, we're going to ignore most of them for now. We've seen the extended ACL already. The other main one is the standard ACL. This is the first one that Cisco created and is much simpler. The standard ACL can only match based on source address. That's it. It can't look at the destination, the protocol, or the ports used. I prefer extended ACLs myself, but you will see standard ACLs out there. One way we can configure ACLs is to give them a number. We configure each entry individually, and any entries sharing the same number are part of the same ACL. This number also determines if this is a standard or extended ACL, as you can see in this table. If you're looking at doing an exam, I would try to remember these ranges if you can. It wouldn't surprise me if you got a question that related to this. Aside from picking a number in the right range, no particular number is any better than any other number. They just simply act as labels to organize the entries into a list. The more modern alternative to numbered ACLs is named ACLs. In my opinion, these are much better. Every list has a name and acts like a container. Entries are nested inside the container. In addition, there's no ranges or numbers to worry about. During configuration, we simply tell the router if this is a standard or extended ACL. This will probably make more sense when we try it in a lab a bit later on. We now have a pretty good idea about how ACLs are built and what they can do. But on its own, an ACL does nothing. Nothing at all. Right now, the router doesn't know how to use the ACL. After all, it doesn't know that we want to use it as a packet filter. So we need to apply the ACL to one or more of the router's interfaces. When we apply an ACL to an interface, we also have to apply it in a direction. There are two directions, called ingress and egress. Ingress means when traffic is coming into the router. Egress is when traffic is leaving the router. So when we apply an ACL, we apply it to an interface with a direction. Take note though, there can only be one ACL per interface per direction. Let's run through an example. When traffic enters this interface, that's the ingress direction, the ACL will be evaluated. If the ACL allows the traffic, it will continue through the router and eventually need to exit from interface GI0/2. That's the egress direction. We have no ACL applied here, so the traffic will automatically be allowed. Now what happens if the traffic flows the other way? There's no ACL applied to GI02 in the ingress direction, so the packet is allowed. The packet will need to leave from the GI01 interface. There's no ACL there in the egress direction, so the packet will be allowed to leave. You can probably see that it is important to understand the path that the packet takes when you're creating your ACLs. There are two VLANs, 10 and 20, which contain workstations and servers. Each VLAN uses a different subnet. There is a router, configured as router on a stick, to pass traffic between the two subnets. Right now, all traffic is allowed between the subnets, but we want to restrict this a bit. So we're going to attempt two goals. Goal 1 is to block regular HTTP traffic to the servers, but allow HTTPS traffic. Any other traffic to the servers should be denied. Goal 2 is to allow the server, but not the workstations, to manage the router with SSH. Nothing should be allowed to manage the router with Telnet. No other IP traffic to the router should be prevented. The starting configuration has already been done, so we won't need to worry about that. As usual, the topology is downloadable from the website, and I'll put a link in the description. Starting at goal number 1, we're going to create a rule to block HTTP traffic to the servers. If we use the access list command, we can configure a numbered ACL. Here you can see the different ranges we can use. For now, only worry about standard and extended. If we were to configure access list 1, we get the options for a standard ACL. If we try to deny HTTP traffic here, you will see that we don't get many options to choose from. Remember that standard ACLs only match on the source IP address. Instead, let's try to configure an ACL from the extended range. See how we now have many more options? Don't worry too much about all of these. Just focus on IP, TCP, and UDP. We can use IP to allow or deny any traffic between certain IP addresses. TCP and UDP can be used to block or allow specific ports between certain IP addresses. In our case, we want to block HTTP, which uses the TCP protocol. The next step is to configure the source address, that is, where traffic is coming from. We want to block all HTTP traffic. If we wanted to, we could get more specific and only block traffic if it comes from a particular source port, but that's not important for our goal. So we'll move on to the destination IP address. So what destination should we use? Should we create a separate rule for each of our servers? Well, if you look at the topology, you can see that we don't have to, as all our servers are in their own subnet. Can you see now how it's useful to separate our resources by VLAN and subnet? Now we need the dreaded wildcard mask. Don't worry, it's an easy one. We only need to match the 192.168.20 part of our address. We don't care about the rest, so our mask will be 000255. We're at the last part now, which is the matching port number. There's a few options we could use here. The most common option is EQ, which means equals. We use this when we want to match one specific port. Some other alternatives include range, for matching a range of ports, as well as GT and LT, to match ports greater than or less than a particular number. We're going to keep it simple and match one single port. We could write in 80 as HTTP traffic uses TCP port 80, or we can make use of some of the well-known values that iOS has made available to us. At the very bottom of this list, you can see that www is used for HTTP traffic. It really doesn't matter if you use this list or if you just type the number in, they both work. And our first entry is done. We can check this with show access lists. Remember to use the do keyword if you want to run this command from within configuration mode. We now have one access list, number 150, with a single entry. This is good, but our ACL is not done. We now need an entry to allow HTTPS. So we now repeat the process, this time permitting HTTPS, which uses TCP port 443. And while we're at it, we can add a remark to the ACL. A remark is just a comment that makes it easier for us to understand what we've configured later. Looking at the ACLs now, we can see that there are two entries. The new entry has been added to the bottom of the list. The final part of our goal is to block all other traffic to the servers. How do we handle this? It's actually simpler than you may think. Although it's not shown as an entry in our list, there is that implicit deny rule at the end. Any traffic that we haven't matched will automatically be blocked. In fact, we don't really even need a rule to block HTTP, although it can be handy, as you'll see soon. So are we done? Almost. We still need to apply the ACL to an interface, in this case gi0/1.10. For this, we need to enter interface configuration mode and enter the IP access group command. We give it the ACL number and then we give it a direction. This is the ingress and egress directions we were talking about earlier. If we want to verify this, we can use Show IP interface and look for the outgoing and inbound access list entries. And it's difficult to test the results of this in a lab, but we'll give it a try. Over on the workstation, we can use the Linux command curl to try to retrieve a web page from the server. It immediately fails when using HTTP. If we try again on HTTPS, it still fails but with a different message. This message means that traffic is reaching the server, but the server doesn't have a web page to give back. So the ACL is actually allowing HTTPS traffic, but because this is in a lab, it's hard to show that. And how about ping? This no longer works as the traffic isn't getting past the packet filter. That's because of the implicit deny rule at the end of the ACL. I didn't originally intend to block ping, but I've done this accidentally. This should show that when working with ACLs, it's easy to overlook things like this, so it's really important that you test your changes thoroughly. Let's take another look at the ACL on the router. Do you see how each rule now has one match? This is from the traffic that we just generated. This is another way to see that our lists are working. You'll notice though that there's no match counter for the implicit deny rule. This is one reason why sometimes it's useful to create deny rules like we did for HTTP, even though we don't seem to need them. While we're looking at these rules, do you see how each rule starts with a number? In this case, it's 10 and 20. These are the entry's sequence numbers. This shows the order the rules are evaluated in. We can give rules sequence numbers if we want, but if we don't, iOS will automatically assign numbers like it has done here. Now to move on to goal number 2, where we only allow SSH from the servers and not the workstations. If we try SSH on the workstation, you can see that part of our job is already done. The ACL we've already configured is already denying SSH to the router. That's the implicit rule once again. This will also be blocking ping and telnet. To block telnet and allow SSH from the servers, we need to create a new ACL, which we will apply to interface gi0/1.20 later. For some variety, we'll configure this one as a named ACL. Named ACLs are configured with IP access list, and there's no need to worry about number ranges here. We can just use the extended keyword. And now we'll give it a name. We'll call this one Server ACL. This brings us to the named ACL subconfiguration mode. The NACL in the prompt means named ACL. This is quite different to when we configured the numbered ACL. Similar to before, we want to deny telnet traffic from any source. However, the destination IP address is just a single IP, the IP of the router. So to simplify things, we can use the host keyword as the destination and enter our single IP address. This means we don't need to worry about a wildcard mask. The rest of the command is just like the one we saw earlier, but before we issue the command, I would like to show you the optional log keyword that we can put at the end. This is used during troubleshooting. When we add this keyword, the router will create a log entry each time the rule is matched. I don't recommend turning this on unless you need it, as it decreases the router's performance. So I'm going to leave it turned off for this entry. Now we can put in a rule to allow SSH to the routers from the servers. You might think we're done, but there's one more thing to think about. Our goal said that we need to allow any other IP traffic to the router. Right now, the implicit deny rule is blocking all other traffic. So we need to add a rule to allow all other traffic. This is a very simple rule that permits IP traffic from anywhere to anywhere. And finally, we just need to apply this to an interface like we did before. Have we finished now? So close. Our original ACL is also blocking all other traffic to the router. We can easily put in a rule at the end of the list to permit all other traffic, but only to the router's IP. From this, you can see that we can add more rules to an ACL at any time we want. I recommend that you try all of this in a lab yourself, whether with a downloadable lab that I provide or with one that you build on your own.